professor, physician, epidemiologist. I am Dr. Sri Banerjee. Hi, I'm Dr. Sri Banerjee, and in this video, I will be going over enantiomers and the science of smell. Before I start talking about enantiomers, I want to briefly go over what enantiomers exactly mean. So let's go ahead and get started here. So what are they? Well, simply speaking, they're non-superimposable mirror images of each other. So if you think about mirror images, the first thing that comes to mind really, if you're thinking about your hand, and so if you take a mirror image of your hand, even though that is considered an isomer, which means that it has the same structure, the mirror image of your hand, but it's not superimposable. So similarly, chemical structures are behaving the same way. And what really gets interesting is that even though these chemical structures are so similar, they're only very slightly different. The consequences of how we perceive this is actually uh, pretty pretty distant. So one isomer may, for instance, smell a certain way, while the other isomer smells another way. So uh, during festive times and during the holiday season, when you're trying to think about how certain senses, certain smells make you feel or about the effect on mood, you want to be thinking about how chemical structures cause that. So this is why this talk will help you understand some of these things. And also, I want to show some of the connections between the chemical structure and how this is perceived in different cultures. So as I talk, this will become a little bit more self-evident as to what I'm referring to. But for starters, I want you to keep in mind as we're moving forward that this is a type of mirroring that is going on at the chemical level that I'll be showing you. So let's take a look at some of these chemical structures. And even though, this may seem like it's a lot, I'll show you very quickly what all of this means. So let me first take a pen and then show you first all of them. Take your attention to linalool first. And this is actually a really important compound because it's found within the herb lavender. And this is actually an herb that I personally have been growing for many, many years. And there are many types of varieties. For instance, there's the French lavender and English lavender, things like that. So this is the chemical structure. And these are actually representing chemical compounds and the element carbon. So if you think of these as imaginary carbons here. And so I want you to take note about the some of these double bonds. And so I'm just going to introduce the fact that when you have double bonds, you have something called s orbital, and then which is typically circular, and then p orbitals. And p orbitals typically are elongated. So some of you might be going in your heads, what does the p orbital mean? You've never heard of it. Or if I say sp2 hybridized orbitals, that may not mean much. But the fact is that because there are these p orbitals, these double bonds that are between carbon atoms are actually a lot more stable than when you have a single bond. Now, why am I going over some of these things? Some of these fundamental key aspects are really important to understand when we're thinking and talking about how some of these structures play a role in how we perceive this. So now we're ready to be going over a little bit about isomers. And specifically how certain isomers play a role. So let's take a look at the isomer on the left versus the isomer on the right. So coriandrol, which is probably familiar to you if you think of the spice coriander, but there's actually other different various spices which this may be present in. And then the one on the right is licoriol. So depending on the isomer and the enantiomer that you are studying, the odor is different. And if you've ever had coriander and some of the related seasonings and spices, you'll find that this is actually very distinct, even though, as you will note, that this has a hydroxyl group and a methyl group, all the same, except that methyl group is facing the mirroring and hydroxyl group is on the other side. So if you were to superimpose these two on top of each other, they actually would not superimpose, and that is by definition an enantiomer. But what's shocking is that there's such a wide distinction between the two. And as I go over this a little further, you'll see much more clearly that this doesn't actually stop at smells, but also flavors. Okay, so here's something about our perception. So here's a couple of additional compounds that you may be familiar with the name. So Caraway is a very popular sort of aromatherapy scent, and also Spearmint. So these are both have distinct smells, but also are very similar in structure. If you notice here, in fact, you might not even note there's much of a difference, but if you look here closely, then the carbon compound, how it's connected to the carbon compound here is different. So that's the only difference. The angle of this carbon to carbon compound. And this makes the difference between Caraway and Spearmint. So would you have ever guessed that? And so the one on the right, again, if you were to create a imaginary line, and this is the same compound that I showed you in the previous slide, but again, it shows how some of these odors and some of these scents are, even though structurally very similar, but yet have different results. Now this is even more shocking because now we're not only talking about smells but also flavors. And so the sweet taste here, and this is particularly referring to arginine, and so the sweet versus the bitter taste. The difference, in fact, is in a carboxyl group and how this carboxyl group is bound to this carbon group right here. And so you can tell that how this binds makes the difference between bitterness versus sweet. And so the receptors, in fact, within our tongue is divided up in quadrants depending on where the flavor is actually results in the type of perception that you have. Okay, so again, I wanted to go over some of these other types of enantiomers. So limonene, if you have in a specific way, then it will smell like oranges, and then coriandrol versus licoriol. Again, the mirror imaging, and that was reflected. Sometimes people characterize it sweet floral versus the woody lavenders. If you're familiar with some of the different types of lavender, this is how it's perceived, depending on the chemical. So we can't go through and discuss all of these enantiomers without understanding one of the more classical building blocks of many of the different types of compounds, of aromatic compounds that exist out there. And terpenes happen to be one of those persistent compounds. So to understand what it actually is, the basic structure is C5H8. So if you're thinking about what that means, here's the head. And so there's one carbon, and then two, there's another carbon, and then 4 and 5. So, and depending on how you number, sometimes this might be 2 up here, and there might be some switching, but these are the 5 carbons. And so if you want to make another bond, so 1, 2, and so you keep repeating this. And so these are the isoprene units that keep repeating. And believe it or not, some of the isoprene, some of the terpenes that are created actually result in things that you are very familiar with. For instance, one of those is squalene, you might be familiar with, and then cholesterol is actually another end result of terpenes. So if you're thinking about a lot of the plants, then, and gibberellines are some of the basic plant hormones that regulate various developmental processes. I mean, this could be stem elongation, germination, dormancy, flowering, flower development, and even fruit senescence, so ripening of the fruit. So, but in general, a lot of these terpenes are also electron carriers. They're also photosynthetic pigments. So if you're thinking about your carotenoids, your phytols, things like that, these are all basically terpenes. There's so many roles of terpenes. They're wonderful for plant-to-plant communication. So if you're having a time when the leaves are starting to change color, then you want to be thinking about that. So terpenes are ubiquitous. This slide I don't want to be talking too much about, but just to show you how important it is to be not only thinking about the building blocks for how some of the compounds are made. So geranyl pyrophosphate. This is a kind of a middle point. So there are common pathways in biochemistry and in a lot of body mechanisms where certain compounds are created after which certain other compounds are made. So you can look at geranyl pyrophosphate as kind of a common pathway which is being then used to create other important compounds. So just keep that in mind. And then we transition to talking now about also some of the very important terpenes that are not only in plants, but also bees. And so this is the Nasanov gland. And as it turns out, the Nasanov gland creates a lot of different compounds. I'm going to show you systematically how some of these compounds are created, and also, again, demonstrate once more how enantiomers make an impact in changing the type of scent that is generated. And some of my early memories of creating scents in the lab was from an organic chemistry lab about 20 years ago when I first walked in and created my first aromatic substance. I'll be talking about that experience a little bit more later. But again, this is a group of compounds that are generated within the abdomen. And so if you look at the first two compounds, nerol and geraniol, do they sound familiar? If you are familiar with some of the aromatherapy agents, neroli, geranium, things like that, these may sound familiar, but the other thing I want you to keep in mind is that these are ending in all. That means one thing. That means that these are alcohols. So you would immediately be expecting a hydroxyl group at the end. And this is exactly what we're seeing. So the alcohol nerol, so the R, if you think about R as the functional group that is being added at the end, they're called functional groups in chemistry, then the CH2OH is the functional group. Now, if we take the functional group and change it around a little bit, and instead of saying we're going to add an alcohol, we decide to add an aldehyde, right? So this is a C double bond OH. So then, adding an aldehyde, then we call this Z-citral versus E-citral. Now, the only difference is how the angle of this aldehyde. Again, this is meant to be mirror images. So just like in the top, nerol versus geraniol were mirror images and enantiomers, well, Z-citral versus E-citral are also enantiomers. Similarly, instead of an aldehyde, and if we decide that the R group in the third part will be a carboxyl group. So it's C double bond O, and then this is a single bond OH. You can't have a double bond between C and an OH because electronically the electrons would not allow that for that to take place. Certain compounds only have single versus double bonds. For instance, carbon can create a double bond. It can in fact create a triple bond with another carbon atom. So two atoms, depending on which they are, create bonds based on what they represent. Okay, so the final one that I wanted to show you is the farnesol. And so if you actually do a dehydration, some sort of a synthesis, then you can get EE farnesol at the bottom. And so this is a really interesting kind of carrier sort of compound that is created, and you might be familiar with this. So what is really interesting about this Nasanov gland is that it's actually used as a messenger for other bees when they see this to come back to the hive and deposit the honey. And so this is a chemical signal messenger mechanism that is used by insects as well. So what are we talking about now? Just in a nutshell, about geraniol and just another one of these terpenes which has an important role in all of this. So just quickly, it has a sweet rose scent, and I needed to talk about this because it's so it has such a huge relevance in so many areas. And so it's a chemical that is created by plants and animals alike and really play a role in defense. It is protecting the plant against herbivory, other predators, other animals foraging. Also, there's disease resistance, so any sort of viruses that affect plants. So the idea is, if this is something that is so important, so relevant for protecting plants, then why doesn't it, have an impact also in making alterations in the human body as well? At the very least, making alterations and just creating different scents. So, going back to the Nasanov glands that I went over about bees, this is another one of those fundamental compounds that are secreted, and it's used as a way to orient the other bees back. So, just in a nutshell, in summary, spices and scents for festive seasons are having their origin in benzene rings and aromatic hydrocarbons like terpenes. Now you know that, and these have extremely important not only properties for plants but medicinal properties, antimicrobial and anti-fungal properties. Some of these same signals that are used to prevent bacterial formation or fungal formation within plants can also be used for humans, and are being used. For instance, Taxol is a well-known terpene derivative, which is used to combat cancer. Additionally, perception of structure is really important. So as you were seeing, a lot of those enantiomers, they're mirror images of each other. They don't actually have a different chemical structure whatsoever. So if you were to write the number of carbons and number of hydrogens and oxygens that each one of those have, then you would see that there's no difference. The only way you would be able to tell is if you were to draw. And so understanding the visual of this requires metacognition, and that brings me to my final point, that it is really important to take a step back. Sometimes if you need to do a deeper dive into some historical context or some cultural context which you feel is relevant to understanding science, then you may need to go into some understanding of stories, like we did in the development of understanding the historical transmission of the idea of the Ouroboros. And so just understanding how that connects to the kekuli structure and the aromatic hydrocarbons, the benzene ring, was really important to understanding just the basic effect on how we differentially perceive these. And so I hope this has been very useful in understanding some of those things. Thank you for listening.